Today we are going to continue with Fourier Transform, Fourier analysis of systems and signals. So we will cover Fourier Transform and discrete Fourier Transform. So we have already dealing with Fourier Transform for discrete time signals. So we want to make sure that at the frequency domain, it is also discretized. Therefore, it fits very well with our digital device. We can always generate, calculate, and store those values in discrete format. And then we will look into or learn a technique called a fast Fourier transform. Now, every time you are using MATLAB to work a Fourier transform, you are using the command called FFT, right? FFT in MATLAB, FFT of a signal X. Well, FFT stands for fast Fourier transform. So yes, it's a Fourier transform. It is discrete Fourier transform. And it's also fast. Fast in a way, it's computationally efficient because it uses some technique to take advantage of the periodicity of discrete Fourier transform and then make it highly efficient so it can be calculated fast. Last time we mentioned that there are four different kinds of so-called Fourier series of Fourier transform. It's really classified by the signal, whether it's periodic or aperiodic, whether it's discretized or it's continuous time or continuous signal. So here we will start with a Fourier transform on a signal. And the signal is always a discrete time signal. So we are dealing with these DSP. So the signal is discrete in time signal, xn. We know n is an integer. It's just a time index. It's a count. If the signal is aperiodic, so xn is aperiodic. So it's a signal, any arbitrary signal. It's in time. It may not be periodic, it can be any arbitrary signal. So what we are going to do is we are going to use, this is discretized, of course, right? We have all these points, not continuous, but you take all these sample, the value, which is my xn. So the Fourier transform in the direct Fourier transform, we call that analysis equation. So we got a set of xn. I want to find capital X. Because this is aperiodic, therefore I will have in frequency signal, it's continuous in frequency omega, so x omega. And then we have here the analysis equation is a summation, it's an infinite sum of xn times the core, which is e to the power negative j omega n, sum over from n in negative infinity to infinity because it's aperiodic signal. So I need to collect every time domain signal points, signal samples. And then once we did the analysis equation, find this frequency domain value, it is periodic. Now this value is periodic because xn, n time domain, it's discretized, right? In frequency domain, it's periodic with a period of 2 pi. So we can take omega from negative pi to pi or omega from 0 to 2 pi. Once again, why the period is 2 pi? Well, because we are taking the Fourier series, Fourier transform, as a special case of Z transform. It's a Z transform evaluate on the unit circle. So the unit circle has a 2 pi ambiguity. When you travel around from 0 to 2 pi, it goes back to the starting point. So indeed, the period is 2 pi, and we have this 2 pi ambiguity. On the other hand, the synthesis equation, which is the inverse Fourier transform. So we take this frequency domain signal, x, capital X, and because it's continuous value, so we need to do an integration. So integrate over one period of 2 pi. So you can integrate from 0 to 2 pi or from negative pi to pi, x omega times e to the j omega n, j to the e to the power j omega n, d omega, and divide by its period of 2 pi. Then we can recover the original time domain signal xn. So indeed, what we do is we said we in Z transform, this is a complex domain, real part, imaginary part. And integration is integrate from negative pi to pi. So negative pi to pi, just doing like this from here to here. If 0 to pi is going from here all the way to pi. So anyhow, we are going to travel one circle, one in a circle, one circle. So we are doing here now on the unit circle. This is my z to the power n, where z is equal to e to the power j omega. Right? And this is the bridge between Z transform and Fourier transform. So if you look at that, this is indeed, we are doing a inverse Z transform. We are kind of doing a contour integration, but this contour is very specific. It's just on the unit circle and doing 2 pi. And we have this synthesis equation. Okay. Now let's move one step further. If I have a Fourier transform on a periodic signal, so xn, not only discrete time, it's discrete in time, but also periodic. Okay, periodic with a period of n. What we have here is actually the period is nts, where ts is a sample period. So this is a period, t sub p equal to that. So if you just using the integer, that's the integer counter, you say the period is n. And that we call it endpoint DFT, discrete Fourier transform, because its periodic n is not only in time, nts, but I also have here in the frequency domain. Frequency domain is periodic, right? Periodic. But if in frequency domain, I'm also periodic with the count n. And we will see this n is actually 0, 1, 2 of n minus 1. This is actually the frequency count, which is k, is also with a period of n. The analysis equation, okay, the analysis equation is the same thing. I'm taking the time domain signal xn. Now, instead of doing a summation from negative infinity to positive infinity, I'm only going to take one period in time, which ends from 0 to n minus 1. We change a little bit of this chord. It's not, now it's e to the power negative j 2 pi k over capital N times n. And this k is my frequency count. So in frequency domain, we have discretized because you are periodic in time. So frequency domain is discretized. So that will give me capital Xk. Again, k is from 0, 1, 2, 3, all the way to n minus 1. So as we need to make sure that the frequency domain is also periodic. So it's, but also discretized. So it's from 0 to n minus 1. If we compare with the previous analysis equation, first, of course, we know the summation range is different. Now it's from 0 to n minus 1 of one window. We also find out this is different. This is from previous is that is omega n, right? If we flip back, this is j omega n, negative j omega n. Now I have negative j 2 pi k over capital N of n. And therefore, it implies this part is my omega. So omega, equivalently, that is 2 pi k over n. This is omega. So let me draw a little here. What does that mean? If I have a frequency, if I got a frequency here, let's say from 0 to this point is n minus 1. Okay, so that's one period. Now, the original omega is originally the window is 0 to 2 pi, right? So it's continuous. So it's close here. Actually, it's corresponding to n here, not n minus n here, 2 pi. So at this point. Here is I have 2 pi, this 2 pi, divide by capital N, and multiply by k. K is count from 0, 1, 2, 3. So you can picture this. We have frequency domain. It's continuous valued. For each one of those, at this frequency is actually 2 pi over n, because you divide 2 pi by n different segments. And then the first one is multiplied by 1. K is equal to 1. This point here is 2 pi over n times 2. K equals to 2. Right? So on and so forth. And this point is 2 pi times n minus 1 over n. So indeed, we have these frequency on a physical frequency domain. They all line up. And then we know exactly that 2 pi stands for, in your case, stands for n here. Stands for this point n here, which is the kind of the beginning of the next window. Okay, so it makes sense. So this k we put in here, indeed, the frequency, original frequency, is written as 2 pi times k over n, because 2 pi divided by n, that's each frequency step, and you times this index k. The synthesis equation is, on the other hand, we have capital X, we want to find little x. Frequency domain x, find the time domain x. So the equation looks very similar, but it's the other direction. Therefore, only we need to change this call. It's exponential to the positive j 2 pi k n over capital N. And we are using a positive term here because this is indeed the synthesis equation. So it's break down into harmonics. This has physical meanings. It just those cosines and the sines. Those are the harmonics, and this is the weight, right? This is the weight, and then you add together, you got your signal. It's a weighted sum. So remember the positive part. Those are the harmonics. It's really in the inverse Fourier transform, because inverse Fourier transform discuss about how do you separate your signal into a weighted sum. And then we have a sum of a constant, that's normalized constant here, and it's 1 over the period, which is n. As I said before, this term, usually you can bring that part here and part here. It doesn't matter. It's just one of constant. It depends on how you define the frequency domain signal. Okay, if you are doing this, the entire summation looks very similar. Everything here is changing of this call. Okay, so this is n samples of the Fourier transform at n equally spaced frequency. Therefore, we call that an n-point DFT. Okay, the period is n. Period is in both time and the frequency. And we also have this. This is, as I mentioned, the omega on this particular frequency pin, or the frequency being the kth omega sub k is equal to 2 pi k over n. Now this is because this equation, these are very similar, and all we need is this part, right? This part and this part. If you can collect all these e to the j 2 pi kn over capital N. Of course, once we got that, I got its conjugate. You can calculate conjugate. And then we have this entire format of a Fourier transform, which is very nice. What I meant here is this can always be calculated beforehand. Right? If you think that, well, I know I want to do an n-point FFT, a DFT. If n is equal to, let's say, 128, I want to do a 128-point DFT. So within a window of time, that's 128 samples. And then within a window of frequency, that's 128 samples. Now, because this can be pre-calculated, right? These can be calculated without knowing the signal X. It's just a number. It's just some values. K and integers, 0, 1, 2, 3, all the way to n minus 1. N is defined. So I can pre-calculate all these and store that in my memory or in my program, in my memory. And then whatever the signal comes in, xn or capital Xk, then I can, using lookup table to take all these exponential numbers and put it in the equation, quickly find your answer, right? So this is exactly what people like DFT, and they can have all these ready and it can work on your signal very quickly. And in this case, okay, so what we mentioned here, now I have a xn e to the negative j 2 pi kn over n, sum over all these, and from 0 to n minus 1, we got a capital Xk, right? So what we need is we need to pre-calculate all these. Now this is simple, we can store that. So if you look at the entire thing, that's xn times e to the power n from 2 pi k times 0 over n plus x1 e to the negative j 2 pi k is still here times 1 over n x2 times e to the negative j 2 pi k times 2 over n. Okay, you got it. Now what we have here is I want to calculate xk. Xk is e to the, let's say k. What about the first one, like x0? The second one is x1, x2, all the way to xn minus 1. Okay, now you know what I want to do. I want to put it in a constant matrix form. So for the first one, x0 is e to the negative j 2 pi. K is 0, k is 0. N is 0, so it's 0 times 0, multiplied by capital N. The second term is e to the negative j 2 pi. K is 0. And then we have a 1 here, so times 1 over n. E negative j 2 pi, 0 times 2 over n. This is going to multiply by signal x0, x1. This is time domain signal, x2, go all the way to xn minus 1. Oops. All the way to n minus 1. Okay, here. All right. And then, of course, this is calculating you'll have a row multiplied by this column and got x0. Now, x1, similarly, we have another row here in this matrix, which is e negative j 2 pi, but this time k is 1. So it's 1 times 0 over n. The second is e to the negative j 2 pi. K is 1, n is 1 over n. E to the negative j 2 pi k is 1 times n is 2 divided by n. Similarly, you know, this row multiplied by this column, and we got x1. And we go this step by step, and all the way to the last row here is e to the negative j 2 pi, where k is n minus 1 times 0 over n. You know, see, 2 pi n minus 1 times 1 over capital N. Okay, and then we know, of course, the last term here is n minus 1 times n minus 1. So we get this. Now, what's good about that? Well, everything here, we can pre-calculate it, right? You give me a capital N, this matrix can be pre-calculated. We call this matrix, actually, we call this a Fourier Transform matrix, just using store that, we are using a matrix form, which is we call F, which this matrix has a dimension n times n. That's the matrix dimension. Now, this part X is a vector. If I'm putting a large vector of this guy, this vector is n times 1, which is the frequency signal vector, equals to the matrix times, and then this vector is the time. This is also a vector, n times 1. This is time signal vector, right? So the Fourier transform becomes very simple. I only need to always store this Fourier transform matrix. Whatever signal you give me, I collect it into a vector. I multiply by this matrix, and then I got the signal in frequency domain. The nice thing, the wonderful thing about this is that the inverse Fourier transform, because everything is just positive with a sign e to the positive j 2 pi kn over n. Therefore, the inverse E transform is exactly this f of inverse. Okay, inverse of this. Multiply by, if you do the inverse, you'll find out it's the same as I'm doing the complex, the Hermitian transpose, the complex transpose. So times capital X equal to little x. These are all vectors. And as I said, this fx inverse difficult to calculate. But in this case, because all this are exponential, this is transpose, is a Hermitian transpose. So you do conjugate transpose times capital X equal to little x. Of course, once you want to do that, you need to make sure this f is defined such that I got a 1 over n square over here. Therefore, all these f and f negative 1 are with the same norm, right? Its only difference is that we have the sign. So now you see it becomes very simple. I don't need to calculate the inverse. So the Fourier transform is this. This is the matrix. Those are the vectors. The inverse Fourier transform is that, the inverse. Okay, it's just two matrix multiplication, and we call this f, which this is the Fourier transform matrix, and it can be easily programmed into the DSP chip or into your program, right? So this is the format of the matrix F. Okay, so I just want to know that's a very simple. Everything is discretized in both time domain and frequency domain. We want to develop a fast algorithm for the DFT, and this is so-called a fast Fourier transform. We use that in all these digital chips, all these DSP, which is digital signal processor. It's already built in. A lot of those Fourier transform work on is they are actually using the engine of FFT. Now let's look at how it works. The analysis equation is this. This is the analysis equation. All I change is I change this code. Okay, I write this as a capital W sub n. Again, as I know, this is only determined by n, capital N, endpoint DFT. So I can always keep it in this as a function of capital N. Then this part is to the power kn, right? This is exactly what we have. We have e to the power negative j 2 pi kn over capital N. Similarly, we can write out the synthesis equation. Synthesis equation is the other way of doing the summation. So we have the signal, which is frequency domain signal capital X. We want to find time domain little xn. We're using the similar code, which is Wn, this Wn to the power negative kn, because Wn, we have a negative sign here. So we have those. And that is the analysis equation and the synthesis equation. Let's write out the analysis equation again here. So we're only working on the kind of the forward direction, and using that to deduct our fast Fourier transform. To calculate one frequency sample, which is calculate each xk, one frequency sample is that is one out of these n samples, frequency samples. We need to n complex multiplications and n minus one complex additions. Now, how do we see that? For each point, I need to do the summation, right? So what I have here is this is the multiplication. So because it's sum, I take n complex multiplications, and then you sum them together. So you have n complex numbers, sum them together. So I have n minus one complex additions. For all n frequency samples, then you just multiply by n. We need a total of n squared complex multiplications and a total of n times n minus one complex additions. So this is, again, this is to the order of n squared of calculations. So if we counting the real multiplications and real additions, which means for all n frequency samples from capital X0 to capital Xn minus 1, we need to use 4 times n squared real multiplications and n times 4n subtract 2 real additions. That's how many calculations I need. Okay. So we conclude that the computational complexity of a DFT, discrete Fourier transform, is proportional to n squared, because this is the highest order, and all the other is just a constant. It's a 4n squared. This is a constant, but we said the complexity is proportional to n squared. And this complexity is like its O complexity of n squared. It's of the order. The calculation is of the order of n squared. This is becomes a problem because n can be large number. Now we are only dealing with if smaller, maybe just 100. If I want to make n very large, let's say 10,000, because I really have your signal xn, which is a finely sampled, and one period has a 10,000 samples, and then I want to bring that into frequency domain, also with 10,000 frequency points within one period, which is within 2 pi. And now this time n square, that's 10,000 square. It becomes quite large. So we will have this a DFT engine will have a lot of computation. So that is a problem because we really have n square. We want to invent some of the Fourier transform, make some innovation steps so can reduce this complexity. One way is using the FFT. And we will find out for FFT, the complexity is proportional to n times log n. Actually, it's log base 2n. Okay, in this, with this complexity. So comparatively, this is much smaller because the log, you just you bring that down a lot. So let me still using this n is 10,000 example. So this time, instead of 10,000 square, now you have a 10,000 times log base 2, 10,000. What is that? How much is that? Okay. We know 1024 is 2 to the power 10. So 20, 48, 496, and then we have 8,192, around that. This is 11, 12, 13. So this is the most is 13 point something, maybe 13.2. I don't know, maybe I just said 13.2. So comparatively much smaller than 10,000. And you multiply by that, you saved the computation a lot. Let's see how we can achieve that reduction in complexity. And we make use of the periodicity of the sequence, this. We know Wn is defined such that it is e to the negative j 2 pi over capital N. Okay. So this sequence, this code itself is periodic with its power k and n. Now let's see. It is actually we know this k only taking value 0, 1, all the way to n minus 1. Of course, it already told us. So if k goes to n, it's periodic. N has a window 0, 1, all the way to n minus 1. And again, it tells us, so if it goes to n, it will have the same effect as 0. So it's periodic. Let's check in this capital W here. So W sub n to the power kn, now we replace that with a capital N. So we write this out. N cancel it out. So we end up with e to the power negative j 2 pi k. K is an integer, and this part equal to 1. So indeed, we have some periodicity here. This is the same as we have as W n k times 0, right? It's 1. We also have this complex conjugate symmetry. So if I'm replacing n with capital N minus little n, so because n is periodic, it's eventually this code becomes 1, so it can remove. So we have W to the power negative j little n, and this is W to the power kn conjugate, right? This is exponential, e to the power something. So you got a negative sign here, it just it's complex and bring the negative to part. This is a symmetry, which means if I look into, let's see, from here, this n from 0 to capital N. Now, my point here, compare with the point of n minus 1. Okay. What I compare is these 2 points is WAN, which is k times 0, WN, k times n minus 1. These are 2 points that's conjugate symmetry. So the absolute value, these two are the same. Now, if these two, they are absolute value are the same. These two absolute value are the same. So it's symmetry around the middle point. And also because we have got that, we already said it's periodic. So k, if I plug this in with n plus n, okay, and then this is period, so it's the same. And I can also putting this capital N on this k, on the frequency count. So k plus capital N is also go back to k. So we have periodicity of this kernel W here. So just keep in mind that this W has this Wn to the power of something has very nice properties, has periodicity, has a conjugate symmetry. Okay. Now let's consider n as an integer of power 2. This n is integer power 2. What we meant is n is either 2, 4, 8, 16, 32, and in this format. Right? It's an integer power of 2. If it is not, what FFT will do, it will take your signal and padding zeros, make the size n is an integer power of 2. What I meant is, if you have xn, you only have x0 all the way to x, let's say 63. What the program meta will do is actually it will padding one more zero, excuse me, to 62. 0 to 62. So I have 63 numbers. So what it will do, it will padding 1 0. Make sure this sequence has 64. N is 2 to the power integer. And then using this entire sequence to do the FFT. All right, so the Fourier transform equation looks like this. We got a time domain signal multiplied by this code, and it's to the power nk, summation n from 0 to n minus 1 of x, that equals to xk. And for each k, we calculate one frequency value, and a k from 0 to n minus 1. So this summation we did n times, right? We changed different k's, we did n times. And then we find each of those x0, x1 to xn minus 1. Okay. I just want to make sure that we understand that. Right? When you calculate that, if later you program anything with DSP, you know you're calculating this sum only find one frequency points. You need to calculate n sums to find n frequency points from x0 to xn minus 1. So we look at this equation. Now I break that into two parts. When n is even, when n is odd. So we break those into two parts. Now I can do that because, yeah, very nice. The n is integer power of 2. So it guarantees I can do that. Change this summation variable. So we change this. You said this is even, n is even. So I'm taking n equal to 2r of the first sum here. So replace this n with 2r. So we have 2r here, 2r here. Then r is from 0 to n over 2 subtract 1. The second part, I am replace that n, because n is odd, replace that with n equal to 2r plus 1. So I plug in, this is 2r plus 1, 2r plus 1, and r is also from 0 to n over 2 subtract 1. Okay. I change a little bit. Here I'm changing this entire thing is an exponential. So we can have exponential. I'm taking this as the base. This as base, and to the power k. I can write this, right? Then I can write this, no problem. And this is because I got 2r plus 1k. So if you do this, you have another term which is w to the power k. So because it's nothing to do with r, so I can move that out of the summation of r. So we got these steps. Now, what is this term? This term is w squared. Wn, we know that's e to the negative j 2 pi over n. So now it's a square, times 2 here. I can bring this 2 to the denominator here. Therefore, it's really, it's also a core, but now I have n over 2 point DFT kind, right? It's here. All right, so just keep that, keep this into my equation. So we have also a w by itself, n over 2 DFT. We write again the previous step. So we have the first part, the second part. Now be careful, but the second part, I got this term is taken out of the sum. I change this into that due to my first line. So I multiply by w, that is n over 2, which is indicated that is a w of n over 2 point DFT. It's again to the power k, rk. Same thing here, to the power rk. So I can call the first term gk. Now this is really a Fourier transform equation. And I call this part hk. The second part, this is also Fourier transform equation, right? Because we got a time domain signal x multiplied by this call. This is x domains, time domain signal x multiplied by this call. And then you sum together with this index r from 0 to n minus over 2 subtract 1. Okay. And we have this step is the gk plus w n to the power k. Now don't forget this term. I always want to make sure that we have this term. Then times another one, hk, which is also from the sum. The sum itself is a format of Fourier transform. The only difference is that the Fourier transform here, now we have this call, It's an n over 2 point DFT. N over this point DFT. And then we need to make sure that we understand the difference. This is the input signal here. These are all the even points, right? This is a time domain, but you count x0, x2, x4, x6. Those are even signals. And these are the odd counted signals. That's x1, x3, x5, so on and so forth. But all these are just input signals. Therefore, from the previous discussion, we know GK is a n over 2 point DFT of even samples of x and x2 to r. HK is an n over 2 point DFT of all the samples x to r plus 1. Now what we do here is, if I can reorder the input, let's just take original n is equal to 8. We reorder that. So we reorder all these. These are the odd counted input samples, x0, x2, x4, x6. These are even counted. These are all counted. So x1, x3, x5, x7. Then this goes to another DFT, which is n over 2 point. In my case, is 4 point now. 4 point DFT. And these are also going through a 4 point DFT. Then we calculate all these frequency output. The frequency output, this one is G0, G1, G2, G3. And this is H, H0, H1, H2, H3. And because we have this previous equation, excuse me, right here, we need to add them together, weighted added. So G0, and coming here, adding a H0, but we have to weight it by Wn over Wn to the power 4. And then these two values add here, we got the output value, which is x4. And if I have G1 here, add H1, and I will have an x5. And similarly, G0, if you're going this, you're adding H0, but you weight it as W to the power 0, and then you get the output X0. So this coming from the previous, the equation here. All right, so I can continue this process because again, n is, we choose that, right? It's 2 to the power an integer. So I can do this, divide again and again. So GK, eventually I can divide into these two. So it becomes a n over 4 point DFT, n over 4 point DFT. But I'm going to reorder the input signal again, reorder the input signal again. For HK, the same. I divide it into an n over 4 point DFT plus n over 4 point DFT. And another difference is that this term, this is the weighted on this, the second term, is become W n over 2 to the power k. Okay. It becomes now, in this case, I continue doing this process. So I reorder the signal again. So remember, originally I have 0, 2, 4, 6. So I'm taking the even counted signal again. So these two, right? These two becomes the input of my first n over 4 point DFT, which is in my case 2 point DFT. And I reordered, now 2 and 6 becomes here. This is all the counted here. And it goes through another 2 point DFT. We find all these values. And these values are also added together, but weighted with Wn to the power 0, Wn to the power 2, Wn to the power 4, Wn to the power 6. And why is this? Well, again, we are using the properties of Wn. Indeed, this part should be this. This part should be Wn over 2 to the power 1. But because this is exponential, I can always square this. So this is equivalent equal to that. This is equivalent to W to the power n. You square both sides. You have a 2 here. what I meant is really you got this 2 pi over n over 2, right? You can bring this n over 2 to the numerator. So we got that. All right, so this can continue. So eventually the last 2-point DFT can also break down into just two values adding together with a weight. And that's a very nice picture. In this picture, everything can be calculated. I don't have any box say this is a Fourier transform, but everything is just connected with this weighted sum of any two branches weighted sum. And this is called a butterfly picture because it looks like butterflies. This is the butterfly. It's called this is a famous butterfly picture of fast Fourier transform. Lastly, what we have here is for this butterfly, we have some properties of this w n to the power n over 2. After few calculation, we know that's -1. And this wn to the power r plus n over 2. After some manipulations of this value, we know it is the negative wn to the power r. So what we want to do is in the m-1 stage to the m stage, these two values, using those two properties, we can also reduce the complexity. It becomes only 1 here. And the other part is multiplied by -1. So we have a butterfly here, but I only need to multiply or weight it once on this branch, weighted by this number w to the power r. And then if you go through here, it just flip the value, and go here, you don't need to do anything. So the symmetry of wn. Therefore, finally, we can write out my original A point DFT into this format. It's a very nice butterfly format. The only thing we need to do is we need to reorder this input. Now it's 04261537. And let's look at the complexity. Complexity is over here in each one of these. The complexity is proportional to capital N. Here is proportional to capital N. Here is the computational complexity is proportional to capital N. And how many of these? Well, how many stages I have? In this case, the stage is really log base 2, 8. I have 3 stages. So that's my log base 2 n. If you have n DFT, I have that many stages. Therefore, the overall complexity is for each stage, I have a complexity n. Then how many stages is log base 2n? So that is the complexity of FFT. Okay, that's how we saved a lot. Okay, I will pause here. Next time we will finish that. So let's see how we can actually make the order correct. Make sure the original signal coming in, it can order in this sequence 04261537.